This is a simple pendulum. We studied this before from energy perspective and from energy perspective. So this is a pendulum. When we have a pendulum like this, the restoring force. So we have two force, one force here, the tension, which doesn't do work. So we don't care about the energy. That because doesn't do work. Why? Because the motion is in this direction, and this force is centripetal, which is along the radius. So has a 90 degree with respect to the motion. There is no work done by that force.
There's no displacement.
This is the displacement is in this direction.
And it doesn't go down.
Yeah. So the work will be the force times the displacement, times cosine of whatever angle, and in that case will be 90 degrees, so will be 0. We care only about the force that brings the tangential acceleration, which is this, not the centripetal. So this is mg. If this is the angle given, theta, so we know that mg, this is mg. If I draw my free body diagram, in always the direction toward the center is my positive direction. That's centripetal motion, which we didn't go over that too much. But when I have the object moving in a circular path, the best way to draw the components of the forces and acceleration is one component in the direction of the center and one tangential. The tangential is this one. So this object is changing the speed due to the tangential component. Since this is mg, this is the angle, this will be my adjacent side of this triangle, this will be mg cosine theta, and the tangential component, which is this, is negative mg sine theta. So you can see here that if this is my right triangle, this will be mg cosine and this will be negative mg sine theta. Why I am putting this? Because I want to derive the equations for simple pendulum. What will be the restoring force? What is the force bringing this object back to the point of equilibrium? And this is the dynamics part, right here. Dynamics, energy, and motion. So in this case, I can say that the restoring force bringing the object back to the point of equilibrium, which the point of equilibrium here is at the bottom. The object that is bringing back to the point of equilibrium, what is the force that is bringing back to the point of equilibrium? Gravity. Gravity along what direction? Mg sine theta. So I can say that the restoring force will be negative mg sine theta. But that we know that is mass times the tangential acceleration, because that's the only force acting along the tangent. So mass cancels out. I can say that AT is equal to negative g sine theta. For small angle approximation, there is in math, there is a formula, a very important formula for our theorem that said that when theta is small, theta is approximately equal to sine of theta, and is approximately equal to tangent of theta. This is called in math the small angle approximation. So I can say that AT, which is the second derivative of the position, in this case second derivative of the position, I can put it as ds, the arm length, over the time, is equal to negative g theta. But theta, if you remember, in terms of the arm length what is in terms of the arc length or the linear distance theta? What was? Omega, no, omega t is theta, but that's as a function of time. How the arc length is related to the theta. Theta r or r theta. Good. What is r here? What is r for the pendulum? The length of the pendulum. So you can see that negative g theta is S over L, the length of the pendulum. So if I substitute here, I get negative g over L S. So the second derivative of the displacement, ds, that is the acceleration, which is negative g theta, but theta is S over L. So now, looking at this equation, which is the differential equation for a simple pendulum, look at the analogy with respect to this equation. So we have the negative, we have the negative, we have x, which is s, and we have the second derivative of x, which is the second derivative of x. Can you see that it's the same equation? Except that I am changing s by L, sorry, s by x. That's the only thing. So I said that if the system follows an equation like this where the acceleration is opposite to the displacement and linearly related to the displacement, is an oscillator. This, you can see that the second derivative of the position, which is the arc length, is opposite to the displacement. Same type of equation. So we can say from here that this is an oscillator. An oscillator where omega will be what? For a simple pendulum, what will be omega? Making analogy, what will be here? A negative omega square x. So what will be omega square here? G over L. So omega square is G over L. So what will be omega? G over L for a simple pendulum. What will be